Hello. In this video I'll be discussing and explaining how you can use orbital diagrams to help explain the first ionization energy discrepancies. So, overall you learned a while back that first ionization energy, is the energy that's required to remove one electron from an atom. And you learned that overall, as you go to the right and as you go up the periodic table, first ionization energy increases, and it decreases as you go to the left and as you go down. However, that's not always the case, and there are several discrepancies in how you can look at ionization energy because it's not always consistent with how it goes. And so what we're going to be looking here today is I've just taken the second row of the periodic table going from lithium to neon, and I've written it out up here. So we start here at lithium and we go all the way down to neon. And for each of these elements, I've drawn the orbital diagram of the valence electrons for that element. So these orbital diagrams just represent the valence electrons for each of these. And I've written each of those beneath in the electron configuration. So right here, for example, I've got the orbital diagram for lithium, and down here I've got the electron configuration for that valence electron. And beneath that, for each of these elements, written in green, is the numerical ionization energy for that element. So for example, the actual first ionization energy for lithium is 520 kilojoules. The actual first ionization energy for beryllium is 899 kilojoules, and so on for each of these. But what I want you to take notice of is the fact that check out boron and oxygen. So check out the energies for boron and oxygen. So we know that as you go to the right on the periodic table, which is what we're doing here as you move across to the right, we know that ionization energy is supposed to increase. But as you go from beryllium to boron, it decreases, because beryllium is 899, boron is 801. And as you go from nitrogen to oxygen, you go from 1400 to 1314 kilojoules. So in these two cases, you're actually going down as you go to the right. But why is that? Why is it for these two elements that their energies are lower than the one that they're next to? And ultimately what we're going to use is the concept of half-filled and completely filled stability in helping to explain why these two elements actually decrease in their ionization energy. So overall, a subshell is the most stable when its orbitals are half-filled or completely filled. So for example, look at nitrogen here. This 2p subshell in particular. So we're going to focus on this 2p subshell. This 2p subshell of nitrogen is considered half-filled. And that's because each of its orbitals up here, each of these three orbitals, contains one electron. One upspun electron per orbital. And what this does is it creates a sort of stability for this. So being half-filled, this subshell is slightly more stable than, for example, carbon. So you notice that carbon has just two, and so that's going to make the nitrogen just that little more stable compared to the carbon because it doesn't have just an empty slot hanging off the end here. But in particular, I want to compare the nitrogen to the oxygen. So you'll notice that the oxygen, for its 2p subshell, has this one downspun electron here. So focusing on this down arrow right here. So essentially, oxygen is one electron away from being half-filled. If oxygen were to lose that electron, the 2p orbital would become half-filled because you would just get rid of that downspun electron and you'd be left with three upspun electrons. And that's why less energy is required to remove that electron. Because think about it like this. oxygen is really close to a sort of stability by being half filled. So the energy required to remove that electron is less because the oxygen would prefer to lose it. So less energy is required. Versus the nitrogen is half filled, which means it has a somewhat of a more stable structure. Which means if you were to remove one of these electrons, you would require more energy because you're taking a somewhat stable structure and you're making it more unstable. So when you make something more unstable, it requires more energy. When you make something more stable, it requires less energy. So when you're making something more stable with the oxygen, it actually requires less energy to remove that electron. Because if you remove that electron, all of a sudden your subshell is half filled. And we're going to notice the same thing for boron. So take a look at boron's 2p subshell. So for the 2p subshell of boron, we've got this one upspun electron here, two empty slots here, and just this one electron sticking out. The same principle applies as with oxygen. It takes less energy to just simply remove that one electron, because if you remove this one electron, then you have an empty orbital up here. And if this orbital up here is empty, this 2s is full. So see how this 2s orbital right here is full. So by removing this one lone electron in the 2p, you can just get rid of the 2p and you're left with a full 2s. So that's why for beryllium, see, beryllium already has a full orbital. So if you were to remove this electron right here from beryllium, the orbital would become more unstable, which means more energy is required to remove that electron. For boron, if you remove this lone electron up here, you're making the boron more stable, which means it requires less energy to remove that one electron. So that's the overall trend with that. So notice with something like neon, so neon is completely full. Neon has a full 8 valence electrons here. So it has a full 2s and it has a full 2p subshells. And because of that, neon has an extremely high first ionization energy. And that's the general trend with the noble gases. So the noble gases all have full subshells for their S and P. And that's going to mean that they have very high ionization energies. It takes a lot of energy to remove just one electron from that, because you're making neon, which is an incredibly stable atom, into an incredibly unstable atom by removing just that one electron, meaning that the energy is higher. And I've just sort of down here drawn out what half-filled orbitals would look like for each subshell. So for the S, you would have just one electron. For the P, you would have 3 upspuns. For the D, you would have 5 upspuns. And for the F, you would have 7 upspuns. So just one upspun per slot means you're half filled. If I were to go through and put the downspun electrons for each of these, then we would be showing a full subshell with all the orbitals completely filled. So hopefully that was, this is one of sort of the magic tricks, I guess you could say, with orbital diagrams with electron configuration. We can use them to help explain some of the phenomenon that we see with the periodic table that we otherwise wouldn't pay much attention to if we didn't have them as a visual guide to show where the electrons are going and why removing them might take more energy for one versus less energy for the other. And it all has to do with stability. The more stable your atom or molecule is, the more energy is required to alter it. The less stable it is, the less energy is required to alter it. So there you go, and hopefully that helps explain that whole phenomenon with ionization energy discrepancies.